All right. Well, you've already, in a sense, I've already started. So I'll jump into a little bit more of the details here. So quite a few years ago, I realized that if I gave a talk and I didn't put pictures on my first slide, I'd forget what I was going to talk about that day. So that's what these are here for. So on the left, you have a picture showing a hydraulic fracture propagation inside of a cage of production wells. It's a method that I'm currently working on called fracture caging that has to do with controlling induced seismicity. And if you were here for some of the earlier talks, you would have heard several people mention how induced seismicity is a pretty significant problem, especially in geothermal energy. So I'm currently in the process of trying to develop solutions to address that. In the middle is an image that comes out of kind of the bread and butter of the work that I do here at Los Alamos. This is a method called Triaxial direct shear. In this case, what you're seeing is an X-ray image, a radiograph, similar to what you might get at a doctor's office, looking through a high-pressure vessel at a piece of shale that's being sheared in direct shear. And the method is called triaxial direct shear because the sample is a cylinder in a core flood style system, so it actually has all three principal stresses are actively pressurized. And then we record a bunch of data from that system to characterize the hydraulic properties and the mechanical properties of these fractures. Later on, I'll show you a video of what this looks like when you're actually watching a fracture break in the subsurface environment. On the right is a picture of myself in the SURF, the Sanford Underground Research Facility at the EGS Coulomb Experiment 1 site. So you can see a bunch of the equipment against the wall there in the mine. And I had the opportunity to get out there and help out, not quite as much, or not nearly as much as some other people on this call, but it was a pretty awesome opportunity to get out there and help out with that project. So there are a lot of people who have contributed to the different pieces that I'm going to show today. So you can see the list of names here, and this is only a partial list. So if you want to see, more of any of the material that I'm going to show today, the best option is to look at the literature. I have papers covering pretty much everything that you'll see here. So since we're here talking about national laboratories, I figured I may as well mention who I am and a little bit of my background. So a mandatory thing that I have to say, because anybody who's a pilot has to tell people that they're a pilot. It's just a fundamental law of nature. So I actually got my pilot's license while I was a postdoc at Los Alamos National Laboratory. So I was able to fit that in with all the work. So it was a pretty neat opportunity. As was mentioned earlier, I got my various degrees at Colorado School of Mines. And then I also did a little bit of studying at University of Canterbury in Christchurch, New Zealand. And that was before they had the earthquake down there. When I was in grad school, I did paragliding quite a bit. So I'd be up in the air, floating around in the clouds. And then I also, played perhaps too many video games, but it did give me good insight and leadership skills, thanks to the types of games that I played. And then if you go really far back in my history, I guess a lot of my early enthusiasm is obvious, because I managed to get an opportunity to drive a full-scale train even when I was only about 13 years old. That was a pretty interesting opportunity. All right, so let's continue here. So as an overview of what I'm going to talk about here is I just want to start off with a single slide that has a lot of snapshots of different things that are going on here at Los Alamos National Laboratory that have had the opportunity to contribute to. And then I wanted to focus on some rock fracture fundamentals. Some of them will hopefully be pretty basic, but it's hard to stress how important some of these fundamentals are as you start to consider more and more complex systems. So I thought it could be useful to some. And then I'll give an overview of the kind of facilities that we use here. And then I'll talk a little bit about fracture caging, that image on the first slide. And then I'll just provide some general takeaways and lessons that I've learned so far in my experience working in rock fracturing and fluid flow. So as far as research subject areas, that I've been involved with at Los Alamos National Laboratory, the one that's been talked about the most today is the EGS Colab project. That's the one on the top left. So that's geothermal energy. I've also been working on developing a design algorithm to more quickly, rapidly optimize well designs and production techniques for geothermal systems. In terms of oil and gas, I've had the opportunity to actually get out to Gaithersburg, Virginia. And at that site, they have a neutron beam that's powered by a nuclear reactor. And we use that to do small angle neutron scattering to look at the microstructure of shales. And I was responsible for operating their high pressure shale environment, which is that silver piece in the middle of the screen in the top image there. More recently, I have been working on fracture branching theory and experimental validation. So here you can see a hydraulic fracture being propagated in a heterogeneous but engineered material. And you can see how you get parallel hydraulic fracture propagation on several different fracture weakness planes as these things propagate. And then in the top right, there's an image showing some work that I did. It was almost more like a side project, but this work was to analyze the shear strength and failure conditions for wells when you're producing and you're getting subsidence in the field, or you're injecting and you're getting uplift. So that's a potential failure mechanism for the cement casing system. And this work was to analyze that. And then in the bottom right, I also have had the opportunity to work on some underground explosions topic areas. That's about all I'm going to say about that for now. So in terms of rock fracture fundamentals, actually, I'm realizing I can't see the chat questions. Is there a way to see that while you're presenting? Does anybody know if there's a way to show the chat window while you're presenting? Okay.
I'm not sure if there is any way, but we'll let you know if we see any questions right away.
Okay, please do, and feel free to interrupt me if necessary.
Thank you.
Okay, so rock fracture fundamentals. So on the left is another image from that hydraulic fracture branching work that we've been doing here. And I like this image because it helps emphasize some of the complexity that you get even when the system is still pretty simple. So, first off, you need to know something about your rock system. You don't necessarily need to know a lot to get useful insights, but you do need to know something about your system. You need to know the state of stress, if possible. You need to know information about the fractures in the site, and you need to know information about the orientation of those features relative to the stress state. At a very fundamental level, this is absolutely crucial information if you want to do any sort of predictions about induced seismicity, stimulation, anything along those lines. Once you do inject fluid at high pressure, or just even lower pressures, you can get into 3 different regimes, and sometimes all 3 at the same time. So you'll have a regime of stable flow, where if you inject at slow rate, and their pressure will never get that high, because the rock formation will be able to accommodate that fluid without rising the pressure, and the flow will just leak off. Conventional oil and gas, basically. In the middle one here, you have a shear slip regime. So in shear slip, you can get into the situation even at low pressures and pressures up to and including the hydraulic fracturing pressure. So there's not really, if you are hydraulically fracturing, you're going to be in the regime where you can also be inducing shear slip. That's kind of an important point that I have found is sometimes under-acknowledged. And then on the right, we have hydraulic fracturing. And Jeff just did a really good presentation on that, so I didn't want to intrude on his turf. Okay, so you have all three of these mechanisms potentially going on simultaneously with perturbations in the subsurface. It doesn't necessarily need to be the pore pressure that's connected to the injection well that's causing these effects. It could be remotely triggered. And it can even be remotely triggered by things as seemingly far-fetched as distant earthquakes or moon tides. So it's good to remember that these kinds of mechanisms can be happening on an almost continuous basis in some places. And then each time that you get stimulation, your fracture network, your fracture system will change, which means if you're doing characterization work, like measuring permeability, injectivity, productivity, you should just expect that these systems are going to be dynamic in nature, that over time, the production from these systems will shift. It can get better, it can get worse. But treating a system, assuming a system is continuous or steady state flow, can sometimes lead you to oversimplify the picture in your mind and lead towards conclusions that might not be as good as they could be. So I think it's important to remember that all these complexities can exist even in systems that are pretty simple. And a lot of this complexity, the underlying elements driving it are things like the heterogeneity of the rock, changing Young's modulus, Poisson's ratio in an X, Y, Z manner. And then pre-existing weak layers and natural fractures, they'll interact with hydraulic fractures in some cases, but not all. And then you have a lot of unknowns in the subsurface. One of the most famous unknowns in terms of stress is the intermediate principal stress. It's notoriously difficult to characterize. And it's even harder to get a really good pinpoint, accurate measurement of that value. So you might have a good estimate of your maximum principal stress and your minimum principal stress. But since you don't know that intermediate principal stress, it's important to acknowledge the limitations of what we can and can't know with certainty. And then there's the other complexity, which is actually what originally attracted me to rock mechanics in the first place, is I really like that in the subsurface, there's nothing excluded. You got hydraulic mechanics, you got poromechanics, thermomechanics, chemistry, seismic stuff, and just general mechanics. So all of these things interact with each other in a coupled manner. And a lot of times, due to necessity, we have to simplify down from that. But in order to best evaluate what you're looking at and the validity and meaningfulness of model results, it's good to keep in mind that fuller complexity that actually exists in the real world. And then I've already talked about the different regimes between stable flow and hydraulic fracturing and shear. But one thing that I'll mention here is in all of my laboratory tests that I've done, characterizing shear fractures and fluid flow through fractures, I have never, ever seen steady state flow, no matter how hard I try to achieve it. I'm starting to think that it basically doesn't exist. There's just too much dynamics going on. All it takes is a little bit of chemistry to precipitate chemical in a certain place and your permeability changes. And this will happen constantly. This kind of challenges does lead to irreproducibility, which is why I go after experiments like you see here on the left, where you can control things as much as necessary to look at the mechanisms that you care about in that particular study. And then finally, there's a multi-scale problem. So there's a lot of different really good numerical models out there that model different parts of, say, hydraulic fracture stimulation or long-term production that don't necessarily directly feed back with each other. So, but in the end, the flow is going to be governed by the smallest constriction in the flow path more so than much else. So, but these flow paths are in the order of, can be sub-millimeter, sub-micron. And if you get into that issue, you have to remember these micron scale effects are going to be controlling systems on the order of kilometers. So keeping that in perspective, I think, is important too. And some models do this in different ways, but it is an important thing to consider directly. So this is very basic, but I need to include this just in case anybody hasn't been thinking about this recently. So in our experiments, Triaxial direct shear, or the conventional, more common experiments of uniaxial compression or triaxial compression, you can get your Morpholum Coulomb failure criteria. Ultimately, this is the most commonly used criteria to predict when slip might occur on natural fractures. If you also include a tensile cutoff term, I find that to be pretty important. It's sometimes neglected by, but well, it can be forgotten sometimes if you're not paying attention to that top possibility. But in hydraulic fracturing, that's the focus area, so maybe not for you guys. And then effective stress. This equation is extremely simple and exceedingly complicated to conceptualize in a more realistic scenario. And poor elasticity is often very non-intuitive in how things behave, and it's easy to make mistakes when considering how effective stress is versus total stresses might apply in different places and different times during the development of a system. And finally, in terms of theory, there's kind of two major branches of theory that cover this topic of predicting slip. One is the seismology, which is generally a strain rate based approach, where they're assuming that things are displacing at some steady rate, and they're looking at the stability between, stick slip, that kind of thing. Then hydrology is more concerned about pressure changes, which is often a little bit more relevant on the timescales of, say, hydraulic fracture stimulation. But both do come together. So in terms of adding on a little bit more complexity here, we can also consider the fracture orientation relative to the in situ state of stress and our uncertainty in characterizing that value. And then we can also consider interconnectivity between different fractures in a system. So on the left is just a classic stereo plot. In this case, I'm showing the critical breakdown pressure for fractures of different orientations. Now, this is not Kirsch solution for a hole in a plate or hydraulic fracture initiation. This is for a fracture that already exists at a given orientation. So if you include the tensile cutoff, you can see that when you have stress anisotropy, you can get into situations where, as you're injecting at a hydrofrac pressure, you're also satisfying the requirements to stimulate shear fractures. So as a hydraulic fracture is propagating along, if it happens to hit a natural fracture, it's weak enough and high enough permeability, the fracture might halt and now start to stimulate that shear fracture, which can play a crucial role in how different stages of an oil and gas well stimulation might interact. They might end up producing from almost the same volume of rock if they all happen to connect not too far away from the injection well through a natural fracture. So they'll end up stimulating the same thing. So remembering those kinds of complexities can be useful. And then on the right here, I'm showing an output from a model that I recently developed that is designed to look at some of these complexities. But here, you're seeing hydraulic fractures being stimulated from different intervals along an injection well. In this case, it's simultaneous stimulation without stress shadowing being considered. And these wells will propagate outwards, and they'll interact with more and more natural fractures as they get bigger and start to leak off to the environment. And in this case, since this is geothermally focused, you actually want these fractures to hit the production wells. You want to get frac hits. And when you do that, you massively increase the leak off, which results in what I've been calling fracture caging, the seismicity control method. So are there any chat questions so far? I'll take that as a no. So moving on a little bit more here, adding some more complexity. So fracture apertures and models like PKN, GDK, they all assume smooth fractures. Real fractures are rough. They're stranded and they're complicated. They're going to have combinations of, they're going to have some shear in them, they're going to have some tension in them. It's not just going to be one pure form or another. This roughness is pretty clearly shown by these results in the right picture here. Granted, this fracture was created by a shearing mechanism, not hydraulic fracturing. But you can see in this case how the aperture is so heterogeneously distributed throughout this system. This raises some complexities because if you have a well that's trying to inject into a fracture like this, and it happens to drill into a portion of this natural fracture that's very tight, in order to get that fracture to flow, you might have to inject at a pressure high enough to tensely open that local area of the fracture. But then as the flow gets further away and hits these more conductive zones, it'll go wherever those zones want it to go. So considering these kinds of heterogeneities and considering that the randomness, in a way, that these kinds of mechanisms introduce will dramatically change how a system performs from, say, one stage to another in a hydraulically fractured well for oil and gas, or whether or not you actually get communication between different wells in a geothermal system. It also has a strong effect on induced seismicity, where if you happen to inject in a way that where most of your fluid goes into the conductive zone that's not being produced from by one of your other wells, that fluid now has a high risk of stimulating larger and larger and larger earthquakes the longer that your project proceeds. So again, I'm mentioning fracture caging. Sorry if I'm sounding like a broken record on that front, but in the bottom left here, you're seeing how the inclusion of these leak-off pathways, in this case being well-type structures, significantly affects how your fracture propagates and grows. In this case, when you have enough leak-off points, you can cause your propagating fracture to just halt, even as you continue to inject at high rate and high pressure.
Hello, Dr. Luke. We have a question in the chat box.
Sure.
Is it possible to capture all these heterogeneities in a frac model? And even if we could, can we properly characterize them?
So that's a really good question, and it's something that I'm actively working on right now. So recently I've been developing a theory to help cover that parameter space of uncertainty, where you can consider things like roughness and stranding in your models. A lot of models, just based on their fundamental assumptions, won't be considering these effects. And that was talked about earlier, I think by Joe Morris, where he was talking about the stranding effect at the hydraulic fracture test site, which was a pretty sound mechanism for what was being observed as like higher toughness than what one would expect for fractures, or higher energy than what one would expect for fracture propagation. So if you don't have those pieces in the model, like stranding, then it won't model those effects. But by including some sort of empirical terms, it's possible that you can include those higher order complexities, even if it's only in a rudimentary, non-indirect way, to better predict more realistic ranges of possibility for ultimate production from a site, for instance. So in short answer, you can include these effects in most models with additional development. And most of the time, these higher order complexities are often ignored. Okay, does that answer the question? I'll keep going. So to better explain the effects of heterogeneous aperture on the flow field, what we have done with our data is modeling the flow with CFD, going through the apertures that we observe in these fractures at in situ conditions. And we like to do it where we don't just consider one flow scenario like X or Y, we consider more than that. We consider different angles of flow, we consider flow through subdomains, to try to better parameterize that possibility space of what might be the connection between hydraulic aperture, roughness, and permeability. So in the top left here, I wanted to include the most commonly used equation for modeling flow through fractures. I have had people get angry at me for showing this equation because they think it's too simple, but it depends upon how you think about it. In this case, I like to use this equation in terms of effective hydraulic aperture. So you're not trying to estimate permeability from a physical aperture. You're estimating a hydraulic aperture from known flow conditions, like pressure and flow rate, using something like an experiment or a numerical model of a rough fracture surface. So that's the way that I like to implement this particular equation. Because very often, the hydraulic aperture can be anything from 80% of the total physical aperture all the way down to 0%. And I'm not exaggerating. It can be 0, even for very large fractures. All it takes is having your injection point and your production point, or either of them, in a place where they don't get good communication with each other. So it's a very high variability in this particular parameter. And then when you consider proppant, I'm actually taking this image from Berkeley. So I'm not trying to claim any credit on this particular image. But when you consider proppant, you have a little bit different scenario because you have these flow channels a little bit more tortuous, and you get proppant crushing and those kinds of things. This is often approximated using something like Darcy's law. But if you look at API proppant conductivity tests, it's important to remember that the theory for what a proppant might do based on size without crushing that kind of effect is way overestimating compared to what laboratory data shows. And I mean, factor of 100 differences. So remembering that discrepancy can be pretty useful. And then on the bottom right, I'm showing an image from my current work where I'm looking at trying to develop you almost want to call it a universal scaling theory to link fracture dimensions to their permeability. But calling it that seems a little bit presumptuous. But that is, in effect, what I'm trying to do right now, to try to better capture the uncertainty of the real world in how we parameterize fractures in models. So here I got a video where you get to see a triaxial direct shear test occurring in my laboratory. In this case, we shear the fracture, and then something that really interesting happens in this one. So if you look at the permeability in green, you can see it decreasing very rapidly over time. And then if you look in the left image, you can see this white material forming in the fracture over time. When we actually did this test, this was not what we were trying to do. We actually had a little bit of barium chloride contamination in our system. And due to a high gradient in the concentration of this fluid in our system, we got very high precipitation that localized in the tightest portions of the fractures. So you got most of the precipitation where the flow is being forced to move the fastest. So this was a very interesting result that we've since done additional work on. But this just helps to show how complicated this stuff can be and how quick it can be. Because if you look at the time scale here, you're talking about a factor of 5 reduction in permeability in only an hour, simply due to barium precipitation. And another thing to remember here is that barium is actually a pretty common element in drilling mud. So these same kind of reactions are not that far-fetched to think of happening in the field. So that concludes my overview of complexities in hydraulic fractures. I only have a couple slides left here, so hopefully make time for questions. But the actual facility that we use here at Los Alamos is a facility that didn't exist when I first got here. So I was able to build this in my time here at Los Alamos. And we have a triaxial system with heat for fracturing our rocks. It has a quad pore system for doing really good geochemistry measurements. In the middle we have some images from the X-ray system that we use that I just showed the video from. And on the right, we have a transparent true triaxial cell where we can actually watch hydraulic fracture propagation over time. We're still in the process of developing this last system, but it's looking pretty promising so far. So as another video here, or actually, is this not a video? It's supposed to be. Oh well, it's like I didn't get embedded properly for some reason. But so since I just showed some on this earlier, I'll just focus on, yeah, we don't need to get into that detail unless there's questions. So to provide a little bit better perspective on the variability in fracture properties, this sequence here is actually five different natural fractures, or 4 different natural fractures, plus a shear-induced fracture in one inch diameter core in our facility. So in this case, we're looking at the evolution of the aperture fields in these fractures as we change the stress conditions, and as we induce a shear fracture, and as we continue to stimulate that fracture. So you can see, starting in row A, the initial fracture in the middle panel doesn't exist. Those lines are actually just an artifact of how computed tomography works with X-ray. So then we generate the fracture, and you get these little strands of fracture forming. And then as you shear it more, they dilate more and more and more. The dilation tends to be in the same general vicinity. So an area that happens to be a little bit dilated initially ends up just growing bigger, but the overall pattern stays about the same, which is pretty interesting to observe. Meanwhile, the natural fractures, they do close a little bit as the confounding stress increases, which is in the F through I regime. But you can't see it super well because it's pretty subtle. So the closure effect is there, but compared to the randomness of the system, the randomness is definitely the winning factor in making things complicated. So
Dr.
now,
Dr. Frash, can I read 2 questions in the question chat to you?
Sure.
So the first question is, how to consider the transition flow from parallel flow to dash flow with propellant in hydraulic fracturing model?
So I think you can actually use either model. It's just a matter of how you want to consider the simplifications and how you want to arrive at the parameters for those models. Because you could use parallel plate flow model with a propped fracture and a correction term to account for how the proppant impedes that flow. And physically, it will be very similar to roughness in a shear fracture, for instance.
Okay. So another question is, can you show some references for your publication about the chemical infilling after the presentation?
Yes, I can provide that. If you have a pen handy, the first author is Menifee, M-E-N-F-E-E. I always spell her name slightly wrong, so it might be slightly different from that. It's Anne Menifee. Okay, so continuing on here, in terms of induced seismicity, which is a topic that mentioned previously, I just wanted to kind of briefly go over what people currently do and what I'm currently working on to add to this work. So overall, the current approach to managing induced seismicity starts with really detailed site evaluation, trying to get a hand on the stress state, the fault lineaments, the potential strengths of those faults, in situ pore pressure, those kinds of things, to estimate how much disturbance the system can handle before it might slip and induce an earthquake. After this, adding on to this, we have the traffic light control system. So these are predetermined criteria before you start injection based on the analysis of the site and future forward modeling. that tell you when to slow down your injection or to stop it or even reverse it, as dependent upon how big of earthquakes you start to observe, where you start to observe microseismicity, and maybe even criterion as simple as if your injection pressure is outside of some predetermined limit. And then that kind of covers the third one there too. So methods that are currently being worked on that I'm familiar with to confront induced seismicity risk are pulsed cyclic injection. These methods involve injecting and then stopping, injecting and stopping to try to reduce basically how much you're doing to the system at a single time, to try to reduce the amount of the potential for a large earthquake in favor of more small earthquakes. And there's good evidence that has been presented at ARMA on that topic. But the method that I've been working on is fracture caging. So instead of relying on site characterization, which has a lot of uncertainty associated with it, fracture caging's approach is to design a well system where you can't really have fractures that miss your production wells. So you put more wells in the system, and you can actually start to take advantage of some economies of scale in this case, because more production wells mean more efficient recovery, which in turn means better control over the system and more power output. So I'll talk some more about that. So here's a video showing injection of colored dyed water into a parallel plate system with 4 production wells. So the production rate and the injection rate are equal. And you can see how the hydraulic fracture, or well, the flow field initially was very rapidly propagating outwards, and then it stalls due to production from those in production wells. It doesn't stop moving outwards completely, but pretty close. And then on the right, to me, this one's a bit more exciting. This is going to show a hydraulic fracture propagating with continuous injection at high pressure into 4 boundary wells. The actual configuration that you're seeing here is the same as what you see on the left. So you can see the hydraulic fracture propagating from the notch in the middle here, and it propagates away. You can see how it slows down over time. That's the radial effect of flow. But as we continue to inject, the fracture ends up stopping completely as it hits each of those 4 wells. When you look closely at this data, you can see that the fracture propagation stops in each well direction as it hits it. So it'll keep propagating in the other directions until it hits those additional wells. So to try to better couple the linkage between what I just showed and controlling induced seismicity, which is a little bit of a leap. I have looked at field data from Japan and Canada and my own laboratory data. And what you can see is when you have more leak off in your system and you're injecting in a steady state, you can get to this kind of plateau in seismic activity if you're recovering enough of that injected fluid. So that plateau effectively appears to be a limit on the maximum magnitude of the earthquake that you'll stimulate during an injection. And right now, this is a working hypothesis, but the idea is that the maximum magnitude will be linked to the length of the spacing between the wells in your system that define the fracture cage. So by changing the size of that cage, you change the maximum earthquake that can be generated by that system. It's probably not 100% foolproof, but so far the observations have been very promising.
Dr. Frash?
Yep.
I read the question in the chat to you.
Mm-hmm.
So the question is from Lotana. So can wells observe hydraulic fractures since fracking is a stress transition, not a flow process?
Can you repeat the question, or can the person who asked the question?
Sure. Can you hear me?
Yes, we can hear you,
Scratchy,
Lotana.
but
Go ahead. Yeah.
Go ahead.
So I was just looking at the fracture caging process you're working on, which is very, very interesting, by the way. But I was just kind of worried. How do you expect wells to stop fracture propagation and growth? Because it's a different process from flow or injection. If it was injection, yeah, the wells would kind of take in fluids, but in fracture propagation, I would think that it's primarily a stress process.
Yes, so caging applies in a situation where you have simultaneous injection and production that's being driven by people. So in terms of natural seismicity, like on the San Andreas Fault, fracture caging, maybe there's some sort of implication there, but it'd be a lot harder to do in a meaningful way, because if you reduce the pressure too much, you can get seismicity. And if you increase it too much, you can get seismicity. So in this case, with caging, it's better not to think too much about the pressure and more about the volume and the flow. Because what it's doing is not controlling the pressure, it's controlling the volume of the fracture that the pressure, that fluid would be creating. And if you look at hydraulic fracture propagation models, ultimately it very much comes down to the volumes. And the pressure is just something that has to happen to get there, but it's not really the driving mechanism for continuing propagation. Not in my experience.
Okay. Thanks for that.
Yeah, so I prefer to think about hydraulic fracture propagation as a volume balance problem versus any sort of stress problem. They're definitely related, and that's why it's in all the theory. But when it really comes down to it, if you're leaking off faster than you're injecting, your fracture is not going to be growing, because if it tries to, the pressure has to drop at those extremes, and it just can't, basically.
Yeah. Oh, okay. Thank you so much for that.
Okay, so this is a good segue into the lessons learned from. Yeah, I've been working on this stuff for 10 years, which isn't a super long time compared to the people speaking prior to me. But so far, what I've observed is hydraulic fracturing pressure, like the breakdown pressure. A lot of times people think of that as the pressure that you have to get up to in order to stimulate a fracture. But in reality, it's more like a cap, because when you're hydraulically fracturing, it's very, very difficult to get much above that pressure limit outside of near wellbore tortuosity and those near well effects. But in the actual fracture itself, it's very, very difficult to get much above that pressure, because as soon as you try to, the fracture grows. Right. So that's one lesson that I've had. And another is, fracture permeability is extremely variable, way more variable than what any analytical model will tell you. So very routinely in our fracture and fluid flow experiments, we'll see the same fracture, simply as a function of time even, swing through 6 orders of magnitude differences in permeability. So these things are extremely variable, and they fluctuate up and down, and but there are limits. The fractures do have maximum apertures, so you can estimate the maximum and the minimums statistically of that range. So for fluid flow, this was mentioned in a way earlier about EGS development. But in fluid flow, the largest, most conductive fracture is what's going to dominate the system. When you consider natural heterogeneity, that brings in a really complicated problem. Because if you want to inject, say for EGS, in an open hole without any sort of zonal isolation technology, what's going to happen in pretty much every case, unless you're very, very lucky, is one major fracture is going to take all that flow. So you have to use different approaches in order to achieve systems that can accommodate more flow in more areas to get better sweep of your reservoir, to get better production. And that's what I'm showing here in the top right plot. And then this is kind of a fundamental lesson in a way of we can't really predict fractures, not very well. we have models that give us good estimates for what the general length might be, height, total aperture. But as far as predicting where an actual fracture is going to go, asymmetry left to right of the well, that predictive capability is a very difficult to achieve goal because we simply don't have the fidelity of in situ data to really be super precise with those predictions. So it's better to design systems that aren't overly reliant on accurate predictions in my mind. And then you don't want to assume that a visible natural fracture is weak. So when you do a well log, like we did at the EGS Coulomb project, we observed a lot of natural fractures that were infilled and mineralized. From doing laboratory testing, we saw that the majority of those fractures, like 80% of them or more maybe, were just as strong as the rock around them and just as impermeable. So if you were to do some sort of model where you assume, shear stimulation, that kind of thing, and you just use some blanket value, like a frictional coefficient of 0.7, you'd be predicting failure on these things, when in reality, they're not going to slip. So actually going through the effort of characterizing these things in certain scenarios could be beneficial. And then hydraulic systems always leak. As a laboratory scientist primarily, hydraulics are you're always there's leaks constantly. It's always a constant battle. And then sometimes they just don't leak, and in the wrong ways. So you kind of anticipate these failures in how you design the experiments to accommodate these kinds of complexities. And then steady state flow is a fantasy. This might be overly presumptuous of me to claim, but I have never seen steady state flow in flow through a fracture, whether a hydraulic fracture or a shear fracture. I just haven't seen it. The closest I've gotten is clean pipes and no rock in the system. But there's always some transients in flow from what I've seen. So I do have additional material I can go on, but at this point, how am I doing on time?
Yes, I think you are already run out of time, Dr. Frash.
Okay.
Yeah.
That's the downside of getting questions while you talk.
Yes.